Okay, welcome to chapter 14, trigonometric applications. We're going to flip this chapter. I'm going to do 3 for the price of 1 today, actually. So we're going to start with similar triangles, and we've seen this before, and so I'm not going to spend a lot of time with it. But basically, if we're in the unit circle, and we have a point on the unit circle, we have a little cute little 90-degree triangle here. Hopefully you can imagine blowing this guy up to be a big triangle. So if we keep everything in proportion and just blow it up to be a big triangle, seeing as this is the same angle here and we have a right angle and a right angle, those guys are what we call similar. So we can basically go back and forth between this point here and this point here as far as its x and y values just by knowing something about similar triangles, and that is if this guy has a hypotenuse of 1 because it's in the unit circle, and say this big triangle out here, we'll call its hypotenuse b, we can basically know something about these x and y for this point b and this point, call it p, on the unit circle just by knowing what goes on when we blow things up or make them smaller when they're similar. We're just basically multiplying. So with that in mind, this value here, this x1, is really just b times the cosine of theta, since the cos of theta is what the value is of x in the unit circle. And so all we're really going to do is take this hypotenuse of 1 and multiply it by whatever this length is, b, the hypotenuse of the big triangle. And for the same reason then, y1, this point out here on the terminal side, is just going to be b times sine theta. So, just an example of that so you can think about it is if A is on the terminal side of an angle in standard position, so these are key words, so if you imagine this, an angle in standard position, so that means we're going to start it from here, and OA equals 10 and theta is 150, give the exact coordinates of A. So I'm going to go out here somewhere, it doesn't have to be perfect, and imagine 150 degrees. I know I'm in quadrant 2. And the length of OA, if this is A right here, is 10. So clearly this is not in the unit circle because it would have to have a radius of 1 if it was in the unit circle. So this thing is like blown out of the unit circle. So like say that was a unit circle here. So we know what this point is because we know something about sine and cosine of 150. So all we have to do then is just multiply what these values are in the unit circle times 10. So the coordinates of the point A are just going to be 10 times the cos of theta, 10 times the sine of theta. And so either we get our calc to help or we remember what's going on. And the cos of 150 is negative radical 3 over 2. And the sine of 150 is a half. And so when we put those values in and multiply those guys out, we get negative 5 radical 5, 5 as the coordinates of this point A out here, which is kind of escaped from the unit circle. Okay, that's all I want to talk about with that. So now the theme of the rest of these notes is this thing called the law of cosines. So if you get out your old reference cheat sheet, I want you to meet something new. This is called the law of cosines. For the purpose of this class, it's not like you have to be able to prove it. You just need to know it exists and be able to use it. And so this is something that allows us to figure out relationships in triangles using trigonometry. So come back to my note sheet here. And if you recall here, the title of this particular chapter is trigonometric applications. So we're going to use equations like the law of cosines and apply them in different situations and see what we can learn. So, from the sheet then, the way it's written on the sheet is a squared is equal to b squared plus c squared minus 2bc cos a. So this is not always going to be, in this form, good for the problem that you have, but, I mean, basically what this would be is some triangle ABC, and if you remember from geometry, usually we identify the sides across from an angle with the small version, so capital A, little a, across from the capital B, little b, big C, little c, often harder to tell the difference, but if you know it's a side, it's little c. And so this, in this form, it helps us work when we know something about the cosine of A, but if necessary, we change it, and I'm going to give you some examples. I'm going to give you an example right now, as a matter of fact. So say that the problem we have is talking about some triangle DEF instead of ABC, and we are asked to actually figure out what the length of D is. So this would be, and it's really just patterns. This would be a situation where we want to take the equation, because our options are either we change our triangle to ABC or we change our equation to DEF. So if really what we want to do is figure out what D is, I'm going to change A to D. So I have D squared equals. And from a pattern point of view, this is A, so I got a B and a C here. So that means I need my E and my F here. So E squared plus F squared minus 2 in pattern, that's all you got to do. I have a B and a C here. This is a B and C, so that means I need to pick up my E and my F times the cosine. I see here is an A, and oh, here's little a, so that means this is going to be the cosine, since this is little d, the cosine of big D. So that would be how you, by sort of this looking at the original, rewrite it so it works for the problem that you're solving. Okay, so let's do a couple problems. Triangle ABC, AB is 8, AC is 10, and cos A is 1/8. Find BC. And I would suggest that drawing pictures is very helpful when we work with this equation. So I'm going to go ahead and draw A, B, C. I'm told that AB is equal to 8, and AC is equal to 10, and I know that the cosine of A, so I don't know what A is, but they're telling me that the cosine of A is 1/8. And my job is to figure out what the length of BC is. So BC is this guy right here, but I'm going to label that little a. Okay, so that means that I want to figure out what little a is, and this is handy because if you look at your sheet, like this would be a nice person making up a question. It's already set up with that a, so I can just use it exactly as I see it on my sheet. So I'm just going to do that. So a squared then is equal to b squared plus c squared minus 2bc cos a, and I'm just going to start subbing in. So, and I'll go ahead and label these. So the side across from the big B is little b, and the side across from the angle C is little c. So in place of b, I'm going to put a 10 and square it. Plus, in place of c, 8 squared minus 2 times 10 times 8. Now, sometimes you'll have angle A and you'll have to write cos of A, but in this case they told us the cos of A, so I can just sub this in directly as 1/8. So I have 100 plus 64 minus, multiply all this stuff out, and you get 20. And so as it turns out, A squared is equal to 144, and so all we got to do is square root both sides, and in this case we don't want the negative since this is actually a length of a side, so A would be equal to 12. And if I want to be more specific to the way the question was asked, BC, then the length of BC is 12. Okay, just another application of it. Diagonals of a parallelogram. So this takes you back to good old geometry. So diagonals of a parallelogram measure 12 and 22 and intersect at a 143-degree angle. So say this is 143. I'm going to draw a better picture here in a second. Find the length of the longer side of the parallelogram to the nearest tenth of a centimeter. So what do I know? If I look at this picture that I've drawn just for scale purposes, this would be my longer diagonal, and from last year hopefully you remember that diagonals bisect each other. So if my longer diagonal is 22, then this could be an 11 and an 11. And my shorter diagonal is a 12, so this would be a 6 and a 6. And so if this is 143, I know that this other measurement here is 180 minus 143, which is 37, clearly smaller than 143. So the side I really want to know is this guy, because it's across from the bigger angle, 143. So I am going to draw myself a picture that I can look at a little better here. So I have an angle here of 143, I have an 11 here, I have a 6 here. So now all I got to do is plug into this. And so when I'm in charge of the problem and I know what the sheet has on it, I'm going to force this sucker to be an A, and which makes me force this guy to be an A. And then I'm going to go ahead and I'll put a B and a C. And that means this is little c and little b. And so then all I have to do is just plug right into this equation. So a squared equals b squared plus c squared minus 2bc cos A. Okay, so little b is 11, so I have 11 squared plus 6 squared minus 2 times 11 times 6 times, this time I actually have to write cosine of A, which is 143. And see, in this situation, you got to make sure you're in degrees or you're going to get an incorrect answer. So, when you, let's see, that's not 36. We'll go ahead here. This is 121, put it in the right order, plus 36 minus 132 cos B. And I would suggest, or I'm sorry, cos 143. Don't round too soon. Don't round until you get to the end, because this is asking you for the nearest tenth. So in the end then, when you do your rounding, you get 16.2 centimeters. So that's after you get what a squared is equal to and you take the square root. I'm having a little space issue here, so I'm just going to cut to the grand finale. I would suggest you punch that in and make sure you agree with what I'm coming up with here. Okay, now I feel like I can join 14.3 in here because I'm still going to just use this exact same equation, but instead I'm going to use it to find angle measures. And hopefully, since you see that there's a cosine in that equation, we can actually fill in all the sides and figure out what an angle is instead. So in triangle, if I can get my page to extend. Okay, in triangle ABC, so once again, pictures help. So here I go, triangle ABC. It doesn't really matter how I draw it because it's just for orientation purposes. A is equal to 12, B is equal to 8, and C is equal to 6. Find the cosine of C. So this is one of those situations where if you go to your cheat sheet, you look at that and you're like, oh no, it's not cosine of C, it's the cosine of A. But I don't care, because I can just go ahead and say, well, I'm going to change that to C, because I need to find the cosine of C. And by this whole pattern thing, then I see, well, oh, okay, that's going to be C squared. And then I see I just need my other variables in this case, so I would need an A squared plus a B squared minus, and just doing the whole pattern thing, I get 2AB cos C. So I can make that equation work for whatever the heck I am doing. Okay, so C squared equals A squared plus B squared minus 2AB cos C. And now, personally, you could just plug the numbers in here and let this problem play out. But when I know I'm trying to find cos C, I kind of like to actually solve the equation and then plug in. So I'm going to go ahead and solve this equation and get cos C alone. So I'm going to take this whole negative 2AB cos C and ship it to the other side. So it becomes a positive 2AB cos C is equal to A squared plus B squared. So I'm doing some algebra here kind of on the fly, since we're getting towards the end of the big algebra trig. Hopefully we can handle that. I'm going to ship the C squared to the other side where it becomes negative. And then to get cos C alone, I just need to divide by 2AB. So this way I've actually taken my equation and gotten it so it's in the form that in the end what it spits out is exactly what I want. So just plugging in then, I have the cosine of C is equal to 12 squared plus the side across from the B is 8 squared minus across from the C is 6 squared, all divided by 2 times A, which is 12, times B, which is 8. And now it's really just pushing the right buttons on your calculator. And in this case I would do that and then hit math, enter, enter, and out comes a 43 over 48. Same equation, just solving it in a different direction. Okay, one last problem. Find the largest angle to the nearest degree in triangle DEF. Triangle DEF. Picture. If DE is equal to 7.5, EF is equal to 9.6, and DF is equal to 13.5. So here's a situation where you need to have an understanding of what the largest angle would be. And so the largest angle then is going to be across from the largest side. So that would be here, angle E. So basically what I want to do is I want to use this equation that I've just created, but make it user-friendly to E, because that's the angle that I want to find. So I'm going to rewrite this as the cosine of E is equal to, and just doing patterns, D squared plus F squared minus E squared all over 2DF. And I'm going to leave this one for you to give a go on your own by trying to plug it in. You're going to come out with cosine of E is equal to approximately, and see if you can get to this place, approximately negative 0.235. Once again, don't round too soon. I would probably keep the whole thing on my calculator. And then E is going to be equal to the cos inverse of that value. And then your calculator will second cos that, and out comes, rounding to the nearest degree, 104. But I would suggest you do this one to make sure that you get what's going on here. That's all I got. Go to MathXL, and there's a few problems there just to see if you're getting this stuff.